Welcome to The Explainer. Today we're going to pull back the curtain on scientific research to look at something that's not a flaw, but actually a feature, error. We're going to explore what it is, how scientists deal with it, and why getting a handle on it is absolutely key to finding the truth. You know, we see those headlines every day, right? Announcing the latest big scientific breakthrough. But we have to ask ourselves, how certain are those conclusions, really? What if the whole process of science, this thing we hold up as the gold standard for objectivity, isn't quite as perfect as we like to think? And here's the kicker. It's not supposed to be. You see, good science isn't about being perfect. It's about understanding that errors can happen, figuring out what kind they are, and then controlling for them. It's that very self-awareness, that embrace of potential error, that actually makes the scientific method so incredibly powerful. Okay, so let's dive right in. To really get a grip on this, you can think of it like computer software. You've got your random, unpredictable glitches, and then you've got those consistent, repeatable bugs. Well, in research, we call these random errors and systematic errors, and they're what scientists are on the lookout for all the time. So, let's start with random errors. Think of these as the little unpredictable hiccups in an experiment. It could honestly be anything. Maybe a participant in a study is in a bad mood, or maybe they're feeling super motivated that day. A loud noise from outside could be a distraction. Heck, maybe they just skipped breakfast. These things are pretty arbitrary, you can't really control them, and they can kind of nudge the results in any which way. Now, this guy is a totally different animal. A systematic error is a consistent, repeatable flaw baked right into the experiment's design. Imagine you're using a stopwatch that's busted, and it always adds 1 extra second to every time you record. That's not a random glitch, you see. It's a built-in bug that's going to skew your data in the exact same way every single time. So here's the key difference you got to remember. Random errors are all over the place, and they mess with the precision of your measurements. Systematic errors, on the other hand, are consistent and they mess with the accuracy. Let's make this super clear with a visual. Imagine you're at a shooting range. If you're dealing with random errors, let's say a sudden gust of wind here, a little twitch in your hand there, your shots are going to be scattered all around the target. They're not in a tight group, so they're imprecise. And since they're all over, they're not very accurate either. Now let's flip that. What if you have a systematic error? Let's say the sights on your rifle are just plain crooked. Well, all your shots might be clustered in a nice, tight little group. Hey, that's precise. But that whole cluster is way off in the top left corner, nowhere near the bullseye. So you are being consistently and precisely wrong. Now look how this impacts the quality of the research itself. Random errors, they just reduce both precision and accuracy. But systematic errors, oh, they are much sneakier. Because they're consistent, they don't actually hurt the study's reliability. I mean, you can get the same wrong result over and over again. But what they totally destroy is the validity, the actual truthfulness of your findings. To see just how easily one simple little error can completely derail an entire conclusion, we have to talk about one of the most famous examples in the history of marketing research. At first, the result was a huge marketing coup for Pepsi. The headline wrote itself, "Even loyal Coke drinkers prefer Pepsi." But then came the twist, and it revealed something absolutely fascinating. The participants didn't actually prefer the cola in cup M. They just had a subconscious preference for the letter M. The very thing they were supposed to be testing, taste, had almost nothing to do with the outcome. That Pepsi story is the perfect setup for our next critical concept. We're talking about those variables that basically crash the party, mix up all the results, and make it pretty much impossible to figure out what's really going on. So an extraneous variable is kind of like one of those uninvited guests just lurking outside the party. It's any factor, besides the one you're trying to study, that could influence your results. For example, if you're studying navigation skills in different age groups, a researcher would have to think about things like, well, how much computer experience do these people have? That could definitely affect the outcome. And a confounding variable? Well, that's what happens when that uninvited guest kicks the door in and starts knocking over the furniture. It's an extraneous variable that you didn't control for, and it did end up having an effect on your results. So in the Pepsi test, the letter on the cup went from being an extraneous variable to a full-blown confounding variable because it, not the cola, is what systematically changed people's choices. You know, all these concepts we've been talking about, from the faulty stopwatch to the Pepsi challenge, they all hinge on this really critical difference between accuracy and precision. So let's just revisit this one more time to really lock it in. This distinction is just so important. So let's recap. Accuracy is all about hitting the bullseye. It's about getting the true, correct value. Precision, on the other hand, is about hitting the same spot over and over and over, no matter where that spot is. That busted stopwatch that's always 1 second fast, it's incredibly precise, but it's not accurate at all. So, why have we spent all this time talking about random errors, confounding variables, and the little details of accuracy and precision? Why does any of this actually matter to you? Here is the most important takeaway. Understanding all these potential flaws doesn't discredit science, it actually empowers us. It makes us smarter, more critical consumers of information. When you know that a confounding variable can offer a totally different explanation for a study's results, you learn to look past the sexy headline and start questioning the method. This is exactly why scientists are so obsessed with replicating studies, to make sure the results actually hold up. So the next time you read about some new study, I want you to just pause and think like a researcher. If a headline claims that people who eat chocolate have better hair, what else could be going on? Could it be their income? Maybe their overall diet is different? Or their stress levels? Just asking that simple question, what's the alternative explanation? That is the first and most powerful step to truly understanding the world around us. Thanks for joining us for this explain.